morning. My name is Nicolas Couder. I am a helicopter test pilot from Thales Avionics. My background as an operational pilot was in the French Navy for almost 20 years. And I'm test pilot since 2008, and I joined Thales 2 years ago. Mainly involved on the avionics program, and I've been involved in the flight testing of this Autopilot program since the beginning, almost 2 years ago. And I am very pleased to present you today the challenges that we, Thales and Standard Aero, faced for the development and the validation of these 4-axis autopilot for light helicopters.
Good morning. So my name is Olivier Lemoine. I am chief architect in Thales. So with 25 years of experience in development and research on helicopter avionics systems, and now more focused on research and technology solutions. So our presentations will be divided in 5 parts. We will first present the context of the light helicopters and the autopilots, then give you some safety assessment on this topic, which will then be illustrated by different cases, situations where we believe a 4-axis autopilot can improve safety. We will see videos that were taken from our flight test done with Standard Aero on our STC called Stable Light, which is a compact autopilot system installed on the A350 or H125. And we will conclude by presenting the different challenges that we met during the development and the validation of our autopilot system. So today, most of you know that in most of the light helicopters there is no autopilot, and in fact there is no 4-axis autopilot existing on these light helicopters. And we also know that a majority of the helicopter accidents and serious incidents concern light helicopters, and we'll see some figures on that. And the last point is that the main key risk area that are met by these helicopters is what we call the aircraft upset or loss of control, for which we think that a 4-axis autopilot can prevent, or at least in most of the cases help to mitigate. So there is a key issue here on safety of flight helicopters, and we think autopilot can help in that case. So if we look at the last EASA annual safety review, so on the left you have the number of accidents for the past decade, showing that we still have a quite important number of accidents per year. And on the right side you have the repartition between light helicopters and medium and heavy. So we see that, at least for Europe, about 90% of these accidents and serious incidents happen on light helicopters. And if we go into more details on the analysis of these different issues, for the 3 main categories: commercial air transport, specialized operations, and non-commercial operations, we see on these graphs, on the horizontal axis you have the number of risk occurrences, and on the vertical axis the risk importance, the risk score. We see that aircraft offset is by far the most important key risk area, followed also by terrain collision and obstacle collision in flight, for which we believe that autopilot can bring significant help. And this is what is reported in this document from the National Transport Safety Board, dated on 2009, which analyzed about 123 helicopter emergency medical service accidents and concluded that for almost half of these accidents, an autopilot or a second pilot would have prevented the accident. And also saying that the use of an autopilot might enhance pilots' ability to cope with high workload, and in particular in inadvertent flight into IMC. And there is also this document, which is more recent, from the US helicopter safety team, that defined 4 pillars to try to reduce the number of accidents on helicopters. And they identified that the first pillar for them is indeed to develop an autopilot for light helicopters because of the high workload during these operations, and in particular in low visibility, low sailing, and unintended IMC conditions. So that's what Nicolas will now illustrate in some situations, practical situations.
Thanks. So, what can bring to safety, for safety and autopilot? First of all, it stabilizes the helicopter. Of course, the most important is to help the pilot in his piloting task, and at least you need a SAS, stability augmentation system, for that. And this is used when the pilot is actually acting on the controls. And for that, to have a real help from the system, you need a real autopilot. When I mean a real autopilot, that with a serial actuator and parallel actuators. So first of all, it stabilizes the helicopter and it lowers the pilot task here in his handling the flight. Secondly, we can say that if the system brings some upper modes, of course, the pilot can give some workload to the mission, and you have available workload that the pilot can use for the mission in a more efficient way. And of course, with the 4-axis autopilot here, we can have fully hands-off operation in both forward flight, also on the transition to the hover, and also in the hover with a full 4-axis autopilot. And then third, we have the system can also provide some flight envelope protection and some dedicated safety features such as go around, automatization of automatic go around, relationship with H-toes that can be done. So that's going to help, of course, the pilot in his task and reduce significantly his workload. So I'm going to try to illustrate all these using some videos that has been taken in Canada for the flight during the flight test campaign. So I'm sorry, some videos are quite poor quality because these are flight test videos and not advertising videos. So the first domain would be the hover domain, and first of all you need to reach to the hover. So the first video is called approach to hover. This is a function that we implemented on the system, and you are going to see that the approach to hover is done fully hands-off. So here the approach to hover has been triggered by a simple click from the pilot on the cyclic. The aircraft is an old IS-350, and you see that during the approach that is controlled fully hands-off, the pilot has the possibility to change the direction of the approach during the transition down or the approach to hover by beeping a button on the collective that changes the direction, but it can also change the glide slope of the approach. For that, of course, this remains a VFR helicopter so that the pilot can change the direction, sees where he's going, but still being safely and fully hands-off during this function. Is protected from the vortex domain also by being fully 4-axis coupled. So the aircraft is going to set into the hover at 50 feet, and you see that the workload of the pilot is quite poor. He's only monitoring the height, monitoring the collective doing his job, and the autopilot is going to automatically revert to the hover mode when into the hover. So you can see the V-hold, velocity hold, and RHT hold modes are on at the end of the approach to hover. And now, when he's here, a simple press button on the go around makes also a safe departure mode from the hover to the forward flight. So the collective is going to raise, and you're going to have a safe increase of the speed and the height of the helicopter. So it's all coupled, and the pilot workload is really decreased during this maneuver. And by the end of the trajectory, the aircraft is set to 65 knots, which is the VY of the IS-350, and a plus 1,000 feet per minute climb. So after the go-around or the departure mode here, the AP revert to airspeed mode and vertical speed mode automatically with this data, so that the aircraft is in safe condition. The second video is almost the same hover domain. So here it's been made on H125 during a vertical magazine demonstration. So the pilot on the right is Roberto's working for Vertical Magazine. So we are in the same time reaching the hover safely. The workload is almost nothing, and it's going to revert to V-hold and RHT, just same mode that we had. And I'm asking Rob to do a lateral translation to the left using the beep. You see once again that the workload is very poor. Both pilots are feet off, hands off almost. So the helicopter is going to the left, and I'm asking Rob to simulate a brownout situation here. So he's making the simulation, and a single press of the go-around during this simulation makes the aircraft fly safely in this situation with a very low workload, almost no workload at all, because the pilot has only had to do a single press button from the hover to depart. And once again, the aircraft is going to set to 65 knots airspeed and plus 1,000 feet vertical speed. He only has to engage the heading mode so that it can go wherever he wants in a safe 4-axis coupling action. So yes, this was the hover domain, and you've seen that the workload has been significantly reduced in the whole task. To go into hover, to hover safely, and then to depart from the hover. So the next domain where 4-axis autopilot is helping a lot is preventing a control flight into Terra in case of degraded visual environment, for instance. I'm going to need the help from Olivier to stop this video because this video is going a little fast, so we're going to do stops in the video to explain that. So first, stop. Thank you, Olivier. So first, the initial image is the aircraft going down at a very high or a high rate. So you're going to see the aircraft approaching the ground, and the H-TOWS system is going to raise a caution first. So the caution will be displayed on the screen using the yellow color. So we're going to have it here. So the aircraft is descending. You have the screen that is displaying the yellow color. So that means the H-TOWS is triggering an alarm, which says to the pilot, "Pay attention! You're approaching the ground." And in this case, the autopilot system is automatically arming the go-around function here. So this is what I'm going to show here with my finger. So the go-around is now armed. And you've seen the red coming on the screen, meaning that it's not only a caution, it's now a warning that is coming out from the HTOS system, saying that he's really going to hit the ground if he's not doing anything. So within 2 seconds, the system, the autopilot, is going to automatically trigger the go-around. And the go-around that you're going to see is not only a go-around reaching 1,000 feet per minute climb, it's going to go around at maximum continuous power climb, so that the aircraft is going to be able to be in safe condition from the ground as fast as possible, and the airspeed is going to be reduced to VY also 65 knots. This is what you're going to see. So now you're going to see the collective going up. As you can see, the go-around has been triggered and the maximum power has been set automatically and safely by the autopilot. The attitude is going to set the speed to 65 knots, and you see the go-around, which could be an emergency go-around in case of approaching the ground. This emergency has been done fully automatically by the autopilot, and this again has been done by the force axis. And then the last video is in case, this is something that is now a little bit common on some autopilot, but still doing good with, and I would say better with 4-axis autopilot. That's the case where the pilot encounters inadvertent IMC. In that case, the pilot workload without an autopilot is very high, is not trained, is not IFR capable, so it needs an autopilot. And here, a single press button on the same button, the same go-around button, is going to put the aircraft in a safe condition here. So sorry for the display of this video, but you're going to see the aircraft at 45 or more degrees here. And in that case, a simple press button on the go-around button is bringing back the attitude of the aircraft to leveling the wings, set the vertical speed to plus 1,000 feet per minute, and the airspeed at 65. So it's, some people call this function a panic button, but it's simple for the crew. Same button, go-around button, is going to do the whole safety features here for the pilot. So same button, simple functions, and the force axis is going to make better than the other ones.
So now some words about the system that is behind. This system is composed of 7 actuators. So we have 3 smart series actuators and 4 trims actuators, the fourth one being on the collective. And we also have a cross-axis architecture that brings safety. We also have modifications on the controls, so the grips and the pedals. And we integrate also a control panel that you have seen on the videos. So this is the main components of this system. And so we have developed, along with Standard Aero, this system as an STC that is currently under FAA validation, which is expected to be finished by the beginning of next year. So some words about the different challenges that we've made during this development. So first we had to integrate our actuators on the helicopter. So all of these actuators were integrated under the deck of the AS350, which was not so complex because we have smart actuators. We don't need any additional autopilot computer. Everything is on the actuators. So it was it was one of the challenges. Then we had to do the human-machine interface design, and in particular the integration of the controls on the different sticks and pedals, which was more challenging on the collective, in particular to be able to manage correctly the auto rotation. Another challenge was related to the performance of the system with the integration and the interface with low-grade primary reference sensors, for which we had to adapt some filterings and monitorings on the different loops of the Autopilot. And finally, we performed hard-over tests, which was simplified by this cross-axis architecture between serial and parallel actuators, so that reduced the failure criticality of our system. So, to conclude, so what we've done, we have developed and we have almost finished this development. So we now can propose a 4-axis autopilot system for light helicopters, which is compact, affordable, and that we think will improve significantly the safety of light helicopter operations. Thank you.
Thank you, Nicolas. Thank you.